syllabus and there's no quiz listed for this 7. I'm not sure. No, she hands it out. It's not listed. Please and thank you. You're welcome. I have it. No, but we did this one last one. So.
I don't have one on me, but.
I did the
Oh, the correction.
corrections,
Cool. Where is everybody today? Yeah, I was wondering. I know calculus apparently killed people on Tuesday, but.
I have a question. So I was watching the lecture from Tuesday, and we were doing this kind of stuff. This last question that we went over, you did log Q. Is it supposed to be log or is it supposed to be natural log?
It should be logged by the time you read-arrive it. So I think,
Oh, okay.
yeah. So that's like the first one is the LNQ with the natural log, and then once this one should be logged. So I might have
okay.
written it there.
Okay, gotcha. Thank you.
All right, found one person. So some people are online. So if you're online, say hello in the chat so I know you're there. So thank you. Let's see. So we'll start off. Come on. There we go. So hopefully you saw my announcement. And just don't forget your pants today. Hey, it's a hot day, so it looks like everybody in here at least has their pants on. So if you're online, don't forget pants. And of course, closed-toed shoes. So we will be back to our regularly scheduled labs today. And then just, sorry, looking in the chat, I won't wear my Crocs this time. So yes, thank you. No holy shoes. And then of course, just reminders, so today is Mental Health Awareness Day. Although it's been Mental Health Awareness Month. But today, I think is a special day. So I'm wearing green, so of course, if you need any help, just let me know. All right, pretty quiet today. I know. Osier's not here, Vaughn's not here, Bradley's not here, all the talkers are not here today. All right, I'll keep an eye on the chat though. So we left off, so we were on gamma emission. And so gamma emission, before we get started though, so I do have today's like cheat sheet. I think we've already seen this, like I said, first quarter, but I just reprinted it in case you didn't have it. So you can kind of remember all the different decays.
Yeah, that's cool.
And then the relevant equations. And so gamma energy are high energy photons. And except when you write out the equations, so there's no loss of particles from the nucleus. So there's not going to be a change in composition. So same atomic number, same mass number. And it's just denoted by this 0, 0 here and then gamma. And so sometimes what you'll see is, you have your whatever atom you're interested in, and it might have a little M by it. And so that M stands for like metastable. And so when you see something like this, this might indicate that it has gamma radiation. And then of course it would just make the X same atom again, plus gamma. So no change, just a lower energy form of whatever that isotope is. And so gamma rays are the least ionizing but have the most penetration. And so what would protect you are lead plates or thick cement walls. And gamma radiation, so this is often used though in like chemotherapy, of like targeted chemotherapy of when they radiate to try to kill cancer cells or whatever else they need to kind of zap essentially with high energy. And they can do that kind of really localized and focused. So that's one big application for gamma rays. And so sometimes this is also tied to some other emissions. So you may see that in a problem that, something undergoes like beta decay and gamma decay. And so then, of course, you could write out the appropriate equation. And so last one's here. So now we have positron emission. And so again, you might see that referred to as beta decay or beta decay positive, so beta positive. And so now it's kind of the opposite of our electron emission. So now it's a positron, so kind of the opposite of an electron. So negligible mass, so there's its symbol, 0 for mass, but then it formally has a +1 charge, and then again, it's like an anti-electron, so you just have our E here. So anti-electron, so it has the mass of an electron, but opposite charge. And again, the mass is negligible compared to the other nucleons. And so, they're similar to beta particles. Again, they can be classified as beta positive, negative, and so it's a beta particle there. And so a positron is formed and ejected from the nucleus when a proton transmutes into a neutron. And so let's look at this nuclear reaction. And so one example is this phosphorus 30. So it can decay to silicon 14. And then, of course, by mass balancing, so of course negligible mass on our beta decay. Then if we have 15 here, so 14, and then +1 gives us back to 15, so we know that that's a positive charge there. And then, so the last one, I can't remember if your book covers this one or not. It's still important, and it comes up less often, but still should be aware of it. And so it's this process called electron capture. And so here's the symbol for an electron, again, 0 mass, right, negative charge formally. And so this occurs when an electron from an inner orbital is pulled into the nucleus. And so you have, right, proton plus your electron, and then that's going to make your neutral particle, your neutron. Welcome, welcome. It's okay, better late than never. And so there's no particle emission here, but the identity of your atom changes since your inner electron then combines with a proton to make a neutron. And so mass number then stays the same, so we can see that, right, mass balancing. But then since we have our positive charge plus our negative charge making our neutron, right, that's going to affect our protons. And so our atomic number decreases by 1, again, changing the identity. And so there's just the cheat sheet that I handed out. And again, you might have already seen it, but if you haven't, it's there. And so now we can look at the equation. So one example of electron captures with this ruthenium 92 here. So it adds an electron. So again, notice mass stays the same, and then we go from ruthenium to technetium. All right, so we saw this yesterday with our nuclear equations. So again, mass is always conserved, and then atomic number is also conserved. And so let's look at this other concept. And if you have questions, feel free to slow me down too. And so we'll look into, so now what is this mass defect? So what is it? And so mass defect is defined as the difference in mass between the nucleus of an atom and the sum of our separated nucleons. So let's look into, well, what the heck does that mean? And so basically what this is trying to do and what we're looking at is how can we quantify kind of the energy in these nuclear reactions? And so let's look at that. And so what's the relationship between like energy and mass? Do you remember that equation? E = mc². Yeah. So E = mc². So now we can analyze how we can use this. So of course that's the famous equation. And so let's look at this. Oh, there's everybody. And so let's focus on, so I'm going to look at bismuth 209 for our isotope. And so I'll give you some information. And so if you look at the mass of this, so looking at the exact mass, it's for this isotope, it's 208.9804 AMU. And so if we want to find the mass defect, what we're going to do is then add up the mass of a proton plus our mass of neutrons and see how it differs from this mass. And so what that means, so for bismuth, so can you tell me, so how many protons does bismuth 209 have? Find bismuth.
83.
So 83, so that's going to be our protons. And then, so if it has 83 protons, how many neutrons does it have? So remember, it's bismuth 209 though, so we got to do some subtracting.
126.
Yeah, so 126 neutrons. So now, right, these are our separate nucleon parts. And so now the next question is, if we multiply this by the atomic mass unit, add it up, what does that give us? And so I'll tell you, so the mass of a proton is 1.007825 atomic mass units. The mass of a neutron is 1.008665 AMU. So go ahead and total this up right now and kind of get what's our expected mass, and then we'll go from there. And I'll type this in as well, so as always, please double check me and make sure I don't make any typos. And so I'm watching the chat as well, so feel free to type your answer. And so when you have an answer, feel free to let me know.
I got one.
What'd you get?
210.741.265.
0.741265. Let me punch that in and see, just verify since, oh my goodness. Perfect, so got the same answer, so I see some nods, excellent. So this is kind of right, our expected mass. And so now we can figure out our mass defect, right? So the difference in mass. So let's just do that subtraction. I don't know why my computer's just a little sluggish today. So now we do the subtraction, so what we calculated minus what we get, from a standard periodic table, looking up exactly what they determined the mass to be. So what do we get for our mass defect? 1.760865. 865, so atomic mass units. Excellent. So now we're here. And so the next step is, how do we relate this back to energy and then quantify how much energy is in each one of those nucleons? And so you all said E equals mc squared. And so I'll give you a constant here, or at least what's helpful. So C squared is 931.5 mega electron volts. And so this is what we use here to relate atomic mass units back to energy. And so again, energy is in mega electron volts. Your mass here is AMU, given this mega electron volts that we're using for C squared. And of course, that's just, right, speed of light squared. So then this gives us 931.5 mega electron volts. And so then we want to figure out our nuclear binding energy. So we can take our mass defect and multiply it by our C squared. So let's get our energy then, because that energy that's missing is that nuclear binding energy that was required then to hold it together, or the energy, right, that's in those nuclear reactions.
I have it calculated.
Perfect, go for it.
1,640.245748.
I'll stop there. So something like 1,640, and so that's mega electron volts for this whole process. So then if we want to get the nuclear binding energy for one nucleon, what do we need to divide by? So how many total nucleons do we have? You might have to like fish through your first quarter brain for the definition of the nucleon. So what number am I referring to?
It's going to be 209.
Yeah, so 209. So remember, your nucleons are just your protons, your neutrons, so that whole number added up. So now we can get the energy then for 1, and so whatever you round it to, I'll just round it to 25 here. And so now mega electron volts divided by our 209.
I got that too.
Oops. And so now we get like 2.848 mega electron volts per each nucleon. So that's how much energy is in there. Questions about that? So I think we're going to shift gears now. So we might come back and hit these equations when we look at practice for homework, but I think we've seen these all before with our half-life. Like we've talked about this. And so I'll just point out, right, this is our half-life equation. So just remember, anytime you see like half-life problems, you use this one. So, right, our first order rate decay. So if you kind of remember, right, our rate chapter, this was the one that we used for half-life. Questions? All right, so now we're going to kind of shift gears completely since, like I said, this is the hodgepodge chapter of our Interchapters. Does everyone have a link, by the way, to the Interchapters? Because those are online. You can like also ask Google, but I can post an announcement too if people haven't found them on Google. All right, so I'll do that. And so our first chapter, so now we're switching gears completely to OChem. And again, if you have other questions about our previous material, just feel free to ask. And so now we're starting with OChem and alkanes. So alkanes are just considered our simplest kind of organic molecules. So they contain carbon and hydrogen. And then if they're alkanes, they're going to be what's called fully saturated. And when we say alkanes, that means that these compounds have no double or triple bonds. So it's all single bonds. And so looking at the acyclic alkanes, so this just means, right, straight chains or any sort of chains. So not making a loop. So it can be branched as well. But as long as you don't make a circle, right, so this would be now a cyclic alkane. So not that. And so all these acyclic alkanes have this general formula. So you can figure out what it would be based upon the number of carbons. So for example, if I said, well, what's the formula for hexane? We're kind of working backwards right now. So hexane refers to the number of carbons. And so if this is straight chain hexane, so if it's a straight chain, that would be denoted as N-hexane. And so this has 6 carbons, so 1, 2, 3, 4, 5, 6. And right now I'm drawing it explicitly just so you can really see what's going on. And so we fill in our hydrogens appropriately, right, so that carbon always has 4 bonds. Then we can count up and see that this formula is valid. So 6 carbons, I'll count again, 1, 2, 3, 4, 5, 6. And then so now counting our hydrogens, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So now plug that into your formula. So we had 6 carbons, and then 6 times 2 is 12 plus 2. So that gives us our formula for hexane. So C6H14. So that's pretty convenient. And then it doesn't matter, too, whether it's like branch. So we'll get into this of isomers. But we can play around with it. So I'll just make one derivation here. So let's see. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so biggest tip for OChem, if those of you that go on to take OChem, is count your carbons. Like count your carbons, like seriously, count them and then count them again. Because like if you're off by a carbon, you know, the whole thing's wrong basically. And also fun fact, I had one of my old students come up to me and say that she really liked my tests because they were difficult and they got you to think, and then it kind of prepared her for OChem where she felt like things were kind of more straightforward and people were struggling. So all these fundamentals really matter here, and counting is super essential in chemistry. It seems so silly, but got to be able to count. All right, so let's see if our formula holds true. So now you want to practice being able to kind of interpret these OChem skeletal structures. So this is generally how organic chemists communicate. They would just show you that, and then you have to be able to determine, yes, that's 6 carbons, and then be able to draw those hydrogens, since remember they don't show the hydrogens explicitly. Instead, you have to know, well, carbon needs 4 bonds, so I need to add hydrogen wherever a carbon does not have 4 bonds, at least explicitly drawn. And so it's only the hydrogens on the carbons that they don't draw. So with nitrogens, like amines, they'll draw the hydrogens explicitly. Alcohols, they'll draw it explicitly. With the carbons, you have to know. And so we'll check our formula again. So C6, then H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it still works, so it doesn't matter how it's arranged. It will still have that general formula. Yeah?
Can you label the carbons on that? Because I still don't understand the structure.
Yeah, so every either endpoint or joint is a carbon.
Okay.
So 1, 2, 3, 4, 5, 6. Other questions? And then so generally, again, if you're practicing how to draw these, so we draw hexane like a chemist would normally draw it. So you kind of do this up-down pattern thing. So 1, 2, 3, 4, 5, 6. So that's how you would draw like a straight chain alkane. So this is hexane drawn like an organic chemist. And they just kind of do this like up-down pattern so you can distinguish between each carbon. So again, every endpoint, right, is a carbon. Every joint is a carbon.
But in reality, that's supposed to be, it's actually a straight line, but it's just how they drew.
Well, yeah, I mean, we'd have to, let's actually just look at a picture, because it is kind of a straight line, but it does do this, right? So you have to think about each carbon has a tetrahedral center, so it does kind of do that little wavy. So let me pull up hexane real quick. Oh, come on. And so this is more like the 3D structures. So this is what it would look like if you were to get like a crystal structure of it. So that's what it would look like in the solid state, right? Each carbon has to have that tetrahedral center. So it does kind of look like that. And so that's relevant. That is often what people say, like, yeah, they look like dogs or something. But what's relevant about that, so thinking back, right, to boiling points and how all that works. So that's how, remember, they kind of stack up. So thinking back, like, to saturated fats. So this is why we call them saturated. So saturated fats, same sort of concept. So since they're like that, since they follow this pattern, they can really stack together. And then, so they have good contact, right? So then good intermolecular forces between them. So that's why your saturated fats are solids at room temperature. So it's all related to that. And so we'll go into unsaturated as we continue. So again, saturated carbons just mean that we have no double, triple bonds. So I'll just write that again so you remember. So no double bonds, no triple bonds, only single bonds. So again, saturated meaning, right, it has the maximum amount of hydrogens as well. And so how we name them is, again, based off of the number of carbons. And so we'll look at kind of more complicated examples. But for example, so we have undecane here, and we use our prefixes, so meth for 1, eth for 2, prop for 3, bute 4, pent 5, hex 6, hep 7, oct 8, non 9, dec 10, undec 11, and dodec 12. And of course, you could continue on and on, so depending on how long your carbon chains go. And so let's just draw out methane. So we know good old methane. And just remember, right, it's tetrahedral structure, so this is kind of our basis. So just recall all those things. So it's tetrahedral. What's the hybridization then on these?
The what?
Thank you.
All right, thanks for coming, Kim.
Oh, enjoy class, have fun.
What was the question?
What's the hybridization?
The hybridization is SP3.
SP3, excellent. So SP3, and so all of these unsaturated are SP3. So then we can draw, right, ethane out, and you can practice, right, you could draw it just like that. That means ethane. Or, so ethane is 2, so 2 carbons if you want to draw it more explicitly. Again, ethane, so all that, the ane endings signify single bonds. So then propane, just straight chain, that's going to be like that. You know, you can draw it like that as well. Propane. And, you know, you could continue to count for yourself to see if the formula holds. And so we can double check right now. So 3 carbons, and then 1, 2, 3, 4, 5, 6, 7, 8. Perfect, so that matches our formula. So 2 times 3 is 6, plus 2, 8. And then butane. Now we could start to have some isomers. So butane, or N-butane, is our straight chain butane. So like that, 1, 2, 3, 4. And again, always count, double count. And then if we look at isobutane, so isobutane is now an isomer. So it has the same chemical formula. So this one, it has 4 carbons, so C4, and then I won't count them up. I'll just use our formula to get to H10. But you can feel free to count them. And so isobutane is going to have our same formula, except now if it's iso, this stands for like this sort of group, where you have a carbon in the center attached to two other carbons. And so there's 1, 2, 3, and then we need one more, so 4 there. And then, of course, don't forget your hydrogens, and I'm just drawing this one since people tend to forget the middle hydrogen there. And so these are, right, our methyl groups. So just drawing out our hydrogens explicitly for everyone. And so structural isomers are then anything with the same chemical formula but different connectivity. So that means, right, completely different. You can pop it off, move it somewhere. So if you had molecule kits, right, you'd be free to completely rearrange however you wanted. And so some of that could be like esters versus alcohols. So you can have like completely different groups too, even though it has the same chemical formula. So something to just keep in mind.
Like homonyms.
Yeah. And so let's see. Let's look at some of the typical reactions they undergo. So of course, we see a lot of combustion reactions with organic molecules. That's pretty standard and something you're pretty familiar with. And so you can, think about your octane burning in your car. That's other combustion reactions that you need on a daily basis. Like your butane running in your house. So all that's combustion reactions. They tend to be fairly inert, though, for the most part, alkanes. They can undergo these substitution reactions. So this is a substitution reaction. And so this occurs under UV conditions. And so if it's UV, that means it's some sort of radical mechanism. We don't have to go too much into detail about, but something like that is with the UV light. It might initiate the reaction, so you have some sort of radical, to make a radical initiator. So you would get chlorine, right? And that's pretty unhappy as a radical here. And then it can go ahead and replace that methane there, so that hydrogen. So you make chloroform plus HCl. So we don't have to know too much about the mechanism, just know that it can do that. And then, so do we remember hybridization, or should we review? Let's at least do a quick recap. So don't forget, right, our hybridization. So we had SP, where just kind of two things are bound to our center atom. And our classic example was like CO2. And don't forget, right, that's our S plus 1p orbital coming together to make our SP hybridized. And then, so sp2, we also saw, so again, some examples of that, or carbonyl groups. So some sort of organic CO. And so, right, that was S plus 2 P's coming together. And then, of course, our favorite, sp3, with our carbon attached to 4 separate things. And of course, tetrahedral geometry, and that was S plus the 3 P's coming together. so now let's look at kind of other functional groups, and then we'll start getting into kind of naming as well. So we'll look at how to name, but then if you see kind of groups off of what we'll call the main chain, this is how you can identify them. So again, methyl is just like a methyl group. So if we're talking about, right, synthesizing meth, that's all that's being added. Sorry, I'm totally blanking on amphetamine. Yeah, so right, they just methylate amphetamine, and that's literally the only difference is a methyl group. So small but very significant. Again, the methyl group helps it cross the blood-brain barrier a lot more readily, so hence why meth is much more potent than amphetamine. And then, so then you have the ethyl group, so that's just, again, 2 carbons branched off. We mentioned propyl, so that's 3, versus the isopropyl. So again, isopropyl, it's a pretty common functional group that people like, so you'll see that. And again, isopropyl with that center carbon, oops, sorry, bound to 2 other carbons. So that's your isopropyl group. And then, of course, right, we can have fluoroderivatives, chloro, bromo, iodo, amine, nitro. So nitro is NO2. So that's a pretty common group. Pretty nasty, though, actually. You don't want to work with nitro compounds, just a fun fact. I mean, maybe you do. So nitro compounds are like really bright and colorful, so that's why people like to work with them. But if they're really bright and colorful, they kind of tend to signify that they're toxic, especially with nitro compounds, so they're kind of nasty things, so just be careful with them. And then we'll look at phenyl groups later, but this is going to be a saturated benzene ring. But all right, so let's look at naming. And I won't try to stump you too much with the naming, so we're just kind of focusing on basic naming for organic chemistry. And so step number 1 is find and name the longest continuous carbon chain. And this is like potentially the hardest step, because sometimes you'll like look at a molecule and you think you're looking at the longest chain, but you really have to keep counting, like where can I go? And you know, it branches off, and we'll practice this, but that's all I'm saying is you have to find kind of the main chain. And so once you identify the main chain, and again, it doesn't have to go in a straight line, it's just however many carbons gives you the highest number.
In like a linear succession.
Yeah, just as long as they're all connected to each other, exactly. So, you know, it looks like it may branch off, but if it's still connected, that's your longest chain. Yeah, so this is a tricky part. And then once you identify the longest chain, you probably want to like highlight it or something. And then you'll identify and name your groups attached to that chain. And then you'll number this chain starting at the end nearest a substituent group. So what this means is we need to give what's called priority to substituted. And again, we'll look at that. And so if there's like, for example, a chlorine or a methyl or something attached to it, that means that it has priority. And we want to give that the highest number. And it may not be 1, you know, it's just whatever the highest number is going to be. And again, we'll go through examples so it makes more sense. And then, so once you have numbered it, then you're free to designate the location of each group by their number. So again, you'll correspond to where it is on the carbon chain. And then you'll name it, listing groups in alphabetical order. And then we'll look at these di, tri, tetra prefixes. All right, so let's look at 1, 2, 3, 4, 5, 6, 7. So that's heptane here. And so before we get to naming, see if you could just write out, like with pictures, all the different isomers of heptane. And so they all have to have this formula, right, C7H16. And so just kind of play around with them, see how many you can write. So there's going to be 9 of them. And then you want to make sure you don't repeat though. And so what I mean by that is, so let's say I do 1, 2, 3, 4, 5, 6. So then if I put my carbon here, so let's say, right, I chopped off carbon number 7. I'm going to attach it to here because that gives us something different, right? It's, what if I do 1, 2, 3, 4, 5, 6? If I put it there, though, it always gets the highest priority. So these are the same, right? So that's what's kind of tricky. Is so these are the same. So if we were to number them, so let's just go ahead and name this one so you can kind of see what I'm saying. So when we go ahead and identify our longest carbon chain, so we could go 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Either way, it doesn't change the name of the molecule. But then, so I'll just pick this as our longest. And then when we name it or start to number it, we want to give highest priority number we can to this group. So that's going to be 2. So 1, 2, 3, 4, 5, 6. And then so to name it, this would be 2-methyl hexane then, right? So the 2-methyl indicates where our methyl group is, and then you just name, right, the rest of the parent chain. And then if we compare that to this structure, right, again, we can see it's the same. So 1, 2, 3, 4, 5, 6. That means this carbon gets a priority of 2. But then when we go to name it, we'll still get 2-methyl hexane. And so they're the same by rotation. So, you know, you could flip them around and see that they're the same. So just kind of be careful with that. But yeah, so go ahead, kind of experiment, try to draw some stuff, and then, you know, make sure that you're not drawing the same thing. It can be tricky. And then we'll try to name what you've drawn. And I will also hand back, so if you haven't been in class, I'll hand back your exam to you so you can do test corrections. Anybody heard from Alexis recently? Hopefully she'll be in lab.
I did take mine yesterday.
Oh, sweet. I've not gotten it yet, but hopefully it'll make its way today then. So play around with it. There are no wrong answers, really. Just make some pretty pictures as long as they have 7 carbons. Does anyone want to draw one of their structures on the board for us or anything? What?
I said not in any way.
Not in any way. Yeah, go for it. It doesn't have to be correct. We just need a starting point. We need something to analyze. I think there's a teal marker. I like it. So let's write that one out. So that's one possibility. And so we'll just count our carbons. So 1, 2, 3, 4, 5, and then 2 methyl groups there. So giving us 7 carbons total. And so how would we name this? So what's our longest chain? So right, count them. 1, 2, 3, 4, 5. Okay, that's one possibility. 1, 2, 3, 4, 5. So either way, it's the same, right? Yes? No? Prove it to yourself if you don't believe me. So let's go the crazy way. So 1, 2, 3, 4, 5, showing you that it doesn't really matter. And so, okay, we know our parent then is pentane. I'm just going to write that at the end. And so let's see, we have to assign priority. And so all that means is we're looking at these 2 methyl groups. So I want to give them the highest number possible. So I could go 1, 2, 3, 4, 5. So that gives them 2 and 3. And of course, just to compare the opposite way, right? 1, 2, 3, 4, 5. So that's not the way we want to go, right? That gives them numbers 3 and 4. We'd rather them be the higher priority of 2 and 3. And so now we can name it 2, 3. And we have 2 methyl groups. So this is what it was saying, right? Your prefixes. So in this case, we have 2 methyl groups. And then we designate them with their numbers. And then dimethyl pentane. All right, do we have another victim who wants to come up and draw a potential structure? What do you have drawn, Sierra? Let's see it. I do want to see. Let's see it. Let's see how weird it is and analyze it. Well, if I made it extra credit, would everybody start running to the board?
Yes, everybody would.
Maybe.
Basically,
I need to take some notes of extra credit. I don't have a pen apparently.
it's like this.
Yeah, I think that looks good. Let me redraw. You're saying you had made up structures. Okay. So let's see. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Sorry, I was like triple, double counting. And we put it there. And so this looks good. So now let's try to assign priority. So we'll do the same thing. So 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5, 6. All right, so this is our priority, our longest chain. And so then we have to try to name it. So if we go 1, 2, 3, 4, 5, 6. So that looks promising. Again, I'll just show you the reverse so you can go through the thought process. Oh, so that's a 4. So that's probably not the right numbering. So we'll go with the green numbering. And so what does that give us then for the name? 3-methylhexane. Perfect. All right, we need some more victims who want to come up to the board. All right, I guess we're offering extra credit now.
You guys are welcome.
Yeah, go for it.
I was gonna go anyway.
Yeah.
What molecule are we drawing?
Oh, we're just trying to draw isomers of heptane. Remember, it doesn't have to be right. We just need something to analyze. All right, I like it. And I like that it's drawn right next to here, so we can easily make the distinction between those two. And so I'll draw it next to our pentane here, trying to group. Sorry, I'm also writing down your names, so do some sort of bonus something. And so, yep, now I'll draw it. Oh, we got another victim. So 1, 2, 3, 4, 5. And then our 2 methyl groups there. And so this one's a little easier to name in some ways, because if you number it, right, 1, 2, 3, 4, 5, that's the same 1, 2, 3, 4, 5, so it doesn't matter which way we go. So 2, 3, 4, 5. And so how would we name this one?
2,4-dimethyl.
Exactly. So you guys are doing way better than you made it sound like. We have our next structure. So 1, 2, 3, 4, 5, 6, 7. So let's see. Let's draw it. I think we might already have that one. And so I'll redraw it, but then you're going to have to check yourself. So then this right, it might not be a correct answer, but we'll go through it together, right? Because I promise there's no wrong answers here. They're just trying to figure out what all our right answers are. So if we look at this one, how it's drawn, so what's our longest chain? So 1, 2, 3, 4, 5. But then what is this starting to look like already? Exactly. So still 2,4-dimethylpentane. So just watch for that. So that's the same. So let's try another structure. So go to B. You can also kind of work through it because you have the heptanes. We have our hexanes. So we can't really do any other hexane variations, right? Because that still gives us 3. So now we're working on our pentane variations. Let's see our next victim here. No victims.
What are you laughing at?
Okay, this looks, let's see how we're looking. So 1, 2, 3. Oh, come on. My computer's like not happy with its life. Perfect. So 1, 2, 3, 4, 5, 6, 7. So that looks good. I don't think it's something we've drawn before. So let's see. What's our highest carbon chain? So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So can we get anything higher than 4? All right, so it seems like, oops. So we have some sort of butane. And you can highlight for your sanity, whichever one you want to look at. And so now looking at how we want to assign priority, I could go, right, 1, 2, 3, 4. And so that's probably the preferred way because we have 2 methyl groups, so we want to give both of them the highest priority possible. And so again, I'll just label the other way, but we'll see that, so 1, 2, 3, 4, and so that's not as ideal, so we want to give priority to the 2 methyls. And so now, how would we name it? So don't forget, now we have 3 methyl groups. We can use our prefixes, right, if we have a bunch of groups of the same kind.
1, 2, 3, trimethyl butane.
Well, it wouldn't be 1 though, right, because nothing's attached to 1, but we have 2 methyls on the 2, so it'd be 2, 2, 3 trimethyl pentane. Butane, sorry, I said pentane, should be butane. Excellent. Trying to mark off who we've done to. 3, till we get all the isomers.
And it has to be linear, it can't connect.
And this can't be a circle.
Gotcha.
So it can be branched any which way. Don't forget you can put other things.
I'm gonna reorient this.
So we're only missing 3. So that's still
Yeah, that's the
2,
same.
3. So what other combinations can we do with maybe these 2 methyls looking at the pentane group? Like how else could we connect them?
We could do-
Nope, now you just made heptane.
Yeah. God, it gets hard.
Anybody think they have the isomers on their paper?
Oh.
Oh, there's one. So yeah, we didn't have that one. So pentane with the,
But that's just hexane.
let's see, so this is one new one, so 1, 2, 3, 4, 5, 6, 7, so 7 carbons. Priority still the pentane. And then we could go 1, 2, 3, 4, 5, or 1, 2, 3, so it doesn't matter, so it's always 3. So now this is 3 ethyl, right, since now it's 2 of them hanging off. So it's an ethyl group, so 3 ethyl pentane. Let's see, I think that's just 3 hexane. Because you have your longest chain, 1, 2, 3, 4, 5, 6. So yeah, that's 3 methyl hexane again. So we're still missing 2. I'll give the hint that they're pentane derivatives. Did you draw anything or?
No, I didn't.
Ah, there we go. There's one of them. So back with the pentane. And then, so that was one combination, is what if we stick both methyl groups on the same carbon? And so there's a pretty similar derivative of that. That's the last one missing.
Would this be one, or is it illegal? It feels illegal.
It feels illegal. Let's see, 1, 2, 3, 4, 5. So this is just 1, 3.
Okay.
Or 2, sorry, 2.
Can you show me that again? How you
All
do
right,
that?
so 1, 2, 3, 4, 5. So then this is 2, 3 dimethylpentane.
Okay.
So then what would this one be named as we try to search for our last isomer? So what's the parent chain on this one? So pentane. Do we write it or? You'll probably be irritated when I give you then dimethylpentane. And so the last one we're missing is we didn't put both these methyl groups on the second one. So that's our last combination is that. So 2,2 dimethylpentane. But excellent job of everyone drawing stuff. Like, that's exactly what you want to do. It doesn't matter what crazy way you draw it, right? But then you have to identify what's my longest chain again, where are my groups, so you can name it and then see, is it just the same? Yeah.
So when you have stuff like, like number or letters in front of organic chemicals, but unfortunately the only one I can think of right now is NN, the dimethyltryptamine.
So NN dimethyl.
What do the N's represent?
What was the last one? NN dimethyl.
Yeah, it is DMT.
Oh, DMT. Drugs, the class now.
Class.
At least the dean has left now as we talk about drugs.
Was it ayahuasca mushrooms that you were thinking of?
No, this is just, I just happen to remember this chemical formula. Hey, man.
So NN dimethyl. Sorry, I'm reading dimethyl. And then tryptamine.
I did a research my paper on psychedelic neurochemistry.
Yeah, so some of these more complicated namings get like weird. So the NN just refers to it's like on there, yeah. Because you would have to know, so NN, so dimethyl, referring to the methyls on the amine, and then of course you would have to like look up this tryptamine group. And then you'll later learn that people come up with all sorts of different names anyways for organic compounds, so naming starts to get more and more complicated. All right, that was excellent. That was fun. All right, so let's see how far we can make it. And so now we're going towards unsaturated carbons. I think that's a new interchapter. So unsaturated. And so unsaturated just refers to the fact that they're technically missing hydrogens in the sense that if you wanted all your hydrogens to be there, you would have, you know, all your hydrogens maxed out. But if it's unsaturated, that means we at least have one double or triple bond. At least one double or triple. And so kind of thinking back to our fats and, well, let's talk about a few things with fats and the different names for it as well. So this is kind of your skeletal structure. of a double bond, except you have two different ways that your double bond could be. And so your double bond, how I drew it initially, is called a cis formation. And so you can imagine that. And cis means the same side. So these are on the same side, the two methyl groups, so that makes it cis. So then, right, you have your chain, your hydrocarbon chain, then it's going to go bloop, and then just keep on going. And so right with that little double bond kink, that messes up those intermolecular forces, right? It can't stack as well. So that's why your unsaturated fats tend to be a liquid at room temperature or so. But then, well, let's talk about trans fats for at least a little bit. And so trans fats are different. I'm not going to go into the synthesis at this moment. But trans refers to, now that the methyl groups are on opposite sides, except if you notice, right, with the trans fat, what can happen, so, right, blah, 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 it's still in the group, trans fat keeps going, so it can still stack. So that's kind of the key with the trans fat, is because of the way it's synthesized, you get this different kink so that it is in line, but that means that your trans fats, right, that's why they're considered to be unhealthy, because they can still stack up and have, right, strong intermolecular forces. And so alkenes specifically, so when you see this ene here, the ene ending, so now that's referring to double bonds. And so now let's practice a few naming scenarios. So we could have this molecule. And so just like before, we want to assign priority to whatever group we have going on. And so we could label it 1, 2, 3, 4. So that's the best way. Obviously, if you went 1, 2, 3, 4, that would give your double bond priority 3, since it would start at the 3. And that's not what we want, right? We want it to be the higher priority. So we want it to start at the 1. So this would be called 1-butene now. And so the 1 just indicates where your double bond starts. And then you have, again, butene, just saying, yes, there's a double bond present there. And so we could draw another version. So then what would this be named?
2-butene.
So 2-butene. And we could even make the distinction, so if you wanted to distinguish, I can scoot this down. So you could have, I'll just redraw this one. So what might you call this one?
2-cis-butene.
Yeah, or it's technically 2-butene, but so cis 2-butene versus trans 2-butene.
So the cis comes first, so the cis trans comes first.
Yeah, if you were making that distinguish. So sometimes, you know, it depends what it is. Like maybe they have a mixture of 2-butene, so then you don't distinguish. Or, you know, if you want to, though, that's where, yeah, you would make that distinction. And so then, so alkyne, so this ine ending refers to a triple bond. And so we could name some alkynes. So 1, 2, 3. So this is a pretty small one. And so, right, the alkynes kind of get weird, so you have to count your points.
Cyanide.
So 1, 2, this isn't cyanide. 3. So I'll just kind of redraw this for a second so you can kind of see how it's drawn out, how to fill in all your carbons. And so it's 1, and you can just call this, right, propyne. Or 1-propyne. label it. Let's see, let's do a tricky one. Yeah, you at least have to have a nitrogen in there to have cyanide compounds.
Yeah, but you got a lot of hydrogens out
Here, so we'll do one kind of tricky one at the very end, since we're kind of running out of time. So let me draw it out. Oh, let me draw it slightly prettier. Sorry, I hate drawing structures. 1, 2, 3, 4, 5. All right, so tricky molecule. Start with what you know, right? Try to find your longest carbon chain. Try to assign priorities. Identify your groups on there.
Are those iodines?
Yes.
Okay.
So for the sake of time, let's at least kind of start going through it together. So what did we find was our longest chain? What did you get?
It was
You said undecane, right? So 11?
I said decane, just in 10.
10, I think people get 10 or 11?
10.
Let's see, so I'm going to count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, these are tricky. I don't like the alkanes either for that reason, or the alkynes, yeah. So then that's 11. So that's undecane. Just trying to remind myself. So undecane, just making sure I spell it correctly. So I'll start with that. Well, it's undecane. Perfect. And so we're still kind of piecing things together. So I'll put, so what priority is the triple bond? What group, or what number, I mean? So 3 undecane. So now we have to piece together everything else in alphabetical order. And so we have a chloro group, so 6 chloro, 8 diiodo, and then this was our longest chain, so a methyl group over there. And so now, right, alphabetical order, you have chloro. Remember, the prefixes don't count, iodo and methyl. And so the last part is put everything in alphabetical order with the number next to it. And so in this case, that would be 6 chloro from our priority. And then 8 diiodo. Oh, hopefully iodo. Sorry, I can't spell. And then last thing, again, alphabetically, is methyl. So then 9 methyl, 3 undecane. And with that, you are ready to name everything. But yeah, we'll do more practice, so we'll have to continue this probably on Tuesday. So we still have some reactions to go over and probably more naming practice. But I think we should go ahead and stop here. So you can take your 10-minute break, and then I have a quiz over, what was it, Echem when you return. All right, so take your break. Bradley, you didn't see my announcement, I guess.
What is it?
You're wearing shorts. Oh, you got pants. Yay, you have pants. All right, and then anyone still in the chat, any questions? I'm going to stop the stream. All right, thanks for being online. I'm going to go ahead and stop this, and I'll see you.